So we're gonna start with the AI gym, and then we do some questions. And people can, okay. So we're gonna do the AI gym stuff. I have it prepared a little bit. And then we're gonna do some questions. And I guess that's it. And if people have, there's the code for the deep deterministic policy gradient, there's the code. There and a little bit of slides which explains what to do at every step, and you can work through at your own time. So this is the DPG code. It's a little bit big. So it's good that we select the AI gym because I don't think we could go through all of this. Okay, so you want to build your own AI gym environment, right? And they have kind of like they have three things, right? They have some kind of init function, and it takes some arguments, right? Whatever you init it with, and you select like, oh, my custom environment. They have like gym environment, and they have like gym continuous environment and gym discrete environment. So if you're a continuous environment like hard pole or mountain hill or whatever, you have like some continuous values. And then you extend the continuous environment, or you have the discrete environment if you're like some discrete game. And here we're gonna look later at Frozen Lake. It extends the discrete environment. Okay, I can stand up. Is that better? People can see me better online.
Would it be possible for you to take a real-life example, as in for some nice thing apart from games?
I haven't prepared it.
Just try anything out of experience.
Can you zoom the code, or it's not possible?
So I can give two real-life examples because people asked for it. I just need something to clean the board. So they're gonna be chatbot with like NLP related. So say you have like chatbot, right?
Can you just repeat the question before you go into it?
So the question was, give an example for a real life problem with reinforcement learning, a real life environment. And there's one thing, you have like a chatbot. So you have like two robots. They want to talk with each other, right? And often if you go to Bell or whatever and you have a problem, you can talk with someone. Nowadays you're gonna talk to a robot. You're not gonna talk to a person right away. And often the robot, they get stuck in problems. One time they just say, okay, like, I don't know. You just repeat, I don't know. Or what is the question? Or sometimes they just end prematurely the conversation. So what they did, they built an environment where, say, okay, you have like kind of a topic related environment, and you're just gonna measure three things, right? You have two robots talk to each other, and they can say whatever, like, hello, my name, and then the other robot says, and the other robot says, the other robot says. And then this is kind of the environment. The environment is these two robots talking with each other. And what you say, okay, next step would be your environment or your state would be the previous thing the robot said, right? I'm not sure if it was just the previous thing what the robot said or the whole conversation, but one of those two things. So it says, okay, yeah, I'm pretty sure it was the previous thing was said, and they always start with some like fixed seed, and then they say, okay, giving this, you're gonna say this, and then you're gonna say that, and then the two robots are trained on the same environment. So the robot always sees the previous chat, and the first robot, he just sees the seed value, the seed message, and then the robot is gonna say something. And then the other robot gonna get the message from the first robot. And then this robot is gonna say something. And it's gonna send it back to the other robot. And the robot gonna edit, and then it's gonna send it back, right? And each time they send it back, they get a reward. And the conversation is done when either like there's they both end the conversation, they both give the end symbol of the conversation, like we stop talking, or these two robots are just talking, like repeatedly saying the same thing over and over again. Then they say, okay, it's done.
Just wondering, how would the rewards be set actually?
So,
Because this will, the response will keep changing, right?
yes, so the reward, they have 3 rewards. So they have a reward, this is the next thing, right? You get your action given a state. And it consists of 3 elements. Say A, B, and C. I don't know the exact equation, but I know what the consists of the element. A is kind of like the length of the, like, you get +1, or kind of the length of the conversation. Like, oh, if you make a sentence, you make a statement that continues the conversation, you get bonus score. If you end the conversation, you're gonna get punished. Then 1 is like the repetition. So you don't always repeat the same thing. Like if you repeat the same thing, and this is like plus, but you think it more like this, minus, minus. So you get reward, a positive reward for continuing the conversation, to keep talking. And then they say, okay, if you just repeat the same thing, like, oh, he says I don't know, and I say I don't know, and then the other one says I don't know, and then I say again I don't know. You just repeat what the other person is saying, we punish you. And the other one is like kind of like a entropy, like kind of like a information content, right? Well, I see. So it's kind of like you're not talking gibberish, because this can also happen. And you just talk, oh, I get rewarded for continuing the conversation. So I'm gonna talk about the weather, I'm gonna talk about my new sports car. Like I don't have a topic. So they say, okay, if your discussion has very low information content or very high entropy, like you just talk about random topics, like random words, then okay, we're gonna punish you as well. And then these 2 agents are trained like against each other just to make the longest, most meaningful conversations. And yeah, that's pretty much it. That's the first example. Oh, I have like many examples now that I think about it. So I can say 2 quickly. Like the other one I like is a lot is about like doing medical report for images. I'm going to go through those in detail, and I have 2 very quick ones. One is like, oh, you have, like say you have an AC, right? You have a havoc system for a whole house or for a room. Yes.
Just a quick question. So about the previous thing, how good are these at the end of it? Can they
so they compared themselves,
or can they actually help? Or
it helps.
okay.
Well, they published. According to them, it helps.
Okay. Is this like often using the real world phenomenon?
I don't think so.
Okay.
I haven't heard of anyone using it. I don't know. Like people use BERG, right? People use whatever these state-of-the-art NLP algorithms. So this chatbot is a bit older. This reinforcement learning chatbot paper is a bit older. They used in vanilla sec-to-sec, and then they use the trained network, and then they they do some special backpropagation. They backpropagate the whole sec-to-sec model for both of those agents, and what they say is, oh, their reinforcement learning sec-to-sec model did better than the sec-to-sec model by itself. And to their evaluation, I would objectively agree that it does better. It makes better conversations. And one thing I heard at a conference once was like blast furnace. So he's from a Canadian company. They help some Canadian company. It's like a steel company. You have to melt steel, and it's like, oh, I barely remember what it looks like, but I will do my best. Like you have some kind of furnace, and you have like some steel comes in, and some coke, like coal, comes in, and you have like certain measures, which is like temperature and pressure, and you have like some steel output. And basically you want to maximize your output while minimizing your input, and still like being safe, that it doesn't have too much pressure or too much like too hot or too cold. And yeah, so there's later a paper, I think I haven't read the paper, but I just saw the paper. It's like about safe reinforcement learning. And they mentioned this, like, oh, if you want to do this kind of blast furnace, you want to train and deploy the model without having the blast furnace explode in your face, right? So you have a self-driving car, or you have this kind of blast furnace or whatever, then you want to avoid catastrophic failure. So, and then there's a whole group of algorithms called safe reinforcement learning, and they deal with this. And I had much time to look into it, but I will definitely do it in the future, and it sounds very promising. And yeah, self-driving car is another example for reinforcement learning, but I'm not it's like the poster child problem for reinforcement learning, but it's kind of out of scope for most normal human beings, like to do things or do things even good. Like they cannot, like Uber and Tesla are struggling with coding a self-driving car, and there's like many problems beyond just the simulation. Like if you have every car a self-driving car, and you have like, if you drive yourself, you realize that maybe you don't even realize, but many times you break the laws, the street rules, because someone is parking in the middle of the street or whatever. There's many special exceptions, and if you remember with the Q learning or reinforcement learning in general, it does really good with states you visit many times. So, but it does really bad with the exceptions. And if you see driving, it's like the biggest problem is going to do if you have to do an exception.
There are also quite unrobust library says every single piece of that is happening.
Yes, but that's like some complete other thing. Like, is that other story? But yeah.
I was going to ask, so, I mean, one of the more popular companies for reinforcement learning being like OpenAI, for instance.
Yes.
So, is the primary challenge for them creating a robust enough like gym environments? Like, is that the challenge?
No, not robust enough gym environments, but robust AIs, right? Like the gym environment, they're like more a static thing, right? For these toy problems, it's like very well defined what the problem is, what it looks like, and building a robust, like, say you want to play Dota, right, or you want to play this game, or you want to do that, then it's like a problem for the environment. Like, say OpenAI and say DeepMind, they're like more research focused, right? They don't actually have a big problem with building the environment, because they deal with like toy environments. There's a group in Alberta, it's also Alberta University of Alberta, does a lot of reinforcement learning, it's the Sutton group. They had a reinforcement learning agent that beat poker. Poker is actually a really complicated game because of the it's like an imperfect game. So most of the games we play,
but it's only in limit. They don't do no limit poker. This is very hard problems.
Yeah. So all these research. Yeah. So all these research groups, what they do research, right? They don't really apply it for a real life problem. And there are a lot of small companies I talked to, I've seen, also big companies that apply this reinforcement learning to real life problems. And on their hand, it's like, can be a challenge to generate the data you need. So there is the NVIDIA research group here in Toronto, and they are having like a mechanical turk and other things for the data generation, and they say, okay, how do you generate training data for the self-driving car? Like they have like hours and hours and hours of recordings, and then they also have like kind of like a virtual environment where they can drive the car and do recordings. Like then you start struggling how to generate like these reinforcement learning algorithms are absolute beasts to train. Say I wanted to train the deep Q learning for say Atari for today. Oh, it just takes 83 hours to train. So I didn't do it in the end because I can't run. Didn't manage to run it through the whole night for three straight days. And so if you want to do the real life problem, it's like, oh, how do you train, say, oh, I have only historic data, right? need like a huge pile of training data, right? And it's either you generate the training data. It's like one of the papers I had in the intersection was mechanical Turk for robots. It's like all these kind of things, like, oh, you know that one of the biggest booming jobs are these like low-paid jobs where you do mechanical Turk for AI intelligence, where you just label data and you generate training data for AI. This is like one of the biggest booming industries, and this is where it comes from. Not only from this, like also for other problems, you just need like huge amount of data. I think that Amazon has a mechanical Turk service where you pay money and they evaluate your model. Like they have a chatbot, mechanical Turk, so they have a person sit down, talk to your chatbot, and gonna mark and say, oh, this is not good, that's good. And that's also, there's not a cheap service, and they need to pay the person to sit down. And
so, can I give an example to that breakdown?
Yeah, sure, go ahead.
So I was trying to implement reinforcement learning for wind turbine.
For what?
So wind turbine.
Oh yeah.
Yeah. So basically, wind turbines, based on the wind that you have, it just tries to adapt itself to which speed it should rotate and like what should be the angle of the blade. So and just like basically, I should mention this. So Sutton, the guy that you mentioned, he has a paper called "Reinforcement Learning is Direct Adaptive Optimal Control."
Yeah.
So that's why like one of the big basically aspects of like reinforcement learning is adaptive control. So for industrial control, like or robot control.
Yeah.
So and the problem there is that like it's not, you can't prove that it's stable.
Yeah.
So that's one of the things that they don't use it.
Exactly.
You can just like.
And if it's not stable,
it's not proven that it's.
Yeah.
I mean, yeah.
But you can have a catastrophic failure, right?
There you
That's
go.
the
Exactly.
problem.
What is the notion of stability here?
So for control systems, stability is like you can go from one state to another state, and basically it converges to that state, and also basically you can prove that it definitely goes there. It doesn't go somewhere else, right? Because let's say your robot arm, right? If it goes overshoots and then it can hit something, it can be very dangerous. But one of the groups that they're working on to solve this problem specifically, it's in University of Toronto. The lady's name I don't remember. She's actually German as well.
I think I know. I think she's,
do you know her?
Yeah, I think I know her.
Mechanical
But
engineer.
But she's
Aerospace department.
maybe another.
They're
place.
working with drones and stuff.
Yeah, I know her.
Yeah.
I talked to her, but
Actually, they have
I think she's Swiss.
cool videos.
Yeah, they have cool videos, yes.
Yeah, so trying to like.
Yeah.
And I think that the other problem is that like if you have real problem, real environment, so you can't basically afford to fail, right? Because as you see during the training at the beginning, it's not trained, right? It can just like damage. What you do usually like make the simulation, train it up to a certain point, and then you probably move to the real environment.
Yes. That's the problem. Like if you have a real world thing, or at the beginning, let's say you do epsilon greedy, right? You just do random epsilon actions for a blast furnace, but are not. A bit of a safety risk here. So yeah. Any other questions? What do you feel like to do? We can ask more questions, or we can look a little bit of the AI gym code. Yes.
Oh, sorry.
One thing, like I think you mentioned it, like making Q learning for a trading card game, and then I looked up. Oh, there is a AI gym environment for Magic the Gathering. There technically is, but the Magic the Gathering, the optimal policy is not computable. So this is. I just looked very quickly, and like you cannot really do reinforcement learning on Magic the Gathering. It's just too complex, especially if you do the deck construction.